Of all the worlds in our solar system, none is more tantalizingly alien, yet hauntingly familiar, than Titan. Saturn's largest moon is a place of impossible landscapes, wrapped in a thick orange haze that has hidden its secrets for centuries. It's a world with a thick nitrogen atmosphere, weather, clouds, and rain, much like Earth. But on Titan, the seas and lakes aren't filled with water, but with liquid methane and ethane, under a sky that glows a perpetual hazy orange. It's a world of extremes, with surface temperatures cold enough to freeze carbon dioxide solid around a bone-chilling minus 180 degrees Celsius. For decades, we've looked at Titan and wondered, could something be alive there? Not life as we know it, but something else, something stranger. Now, the most powerful space telescope ever built has peered into that thick orange smog and found something scientists have been hunting for years. A single, fleeting molecule. A molecule so reactive, so important, that its discovery has just thrown open the door to the possibility that something truly extraordinary is happening on Saturn's most mysterious moon. This isn't just another discovery, it's a vital clue in the greatest detective story of all, the search for life beyond Earth. Before we get to what the James Webb Space Telescope found, let's take a trip to Titan itself. Picture a world larger than the planet Mercury, shrouded in a dense, nitrogen-rich atmosphere 4 times thicker than our own. For centuries, this atmospheric cloak made Titan a complete enigma. All we could see from Earth was a fuzzy orange ball. What was hiding underneath? A global ocean of methane? A solid, icy surface? The mystery started to unravel with the Cassini-Huygens mission. In 2005, the Huygens probe did something incredible. It plunged through Titan's atmosphere and landed on its surface, sending back the first ever pictures from this alien landscape. And what it showed was stunning. A world carved by processes eerily similar to Earth's. There were river channels, shorelines, and vast, dark plains that looked like dried-up lake beds. Cassini, which orbited Saturn for over a decade, used radar to pierce the haze and map out a world that defied imagination. It found vast seas and lakes, not of water, but of liquid hydrocarbons, mainly methane. It found colossal dunes, not of sand, but of solid organic particles, stretching for hundreds of kilometers. And it confirmed that Titan has a weather cycle, much like Earth's water cycle, but with methane. Methane evaporates from the seas, forms clouds, and falls as rain, carving the landscape below. But the real magic of Titan is in its air. The thick atmosphere is mostly nitrogen, with about 5% methane. High above the surface, this methane gets blasted by ultraviolet light from the sun and energetic particles from Saturn's magnetic field. This energy shatters the methane molecules, kicking off a chain reaction of complex organic chemistry. This is what creates the thick orange haze, a smog of complex organic compounds that scientists call tholins. These molecules, rich in carbon and nitrogen, slowly rain down from the sky, blanketing the entire moon in a layer of organic material. This is exactly why astrobiologists are so obsessed with Titan. Its atmosphere is a giant, planet-sized laboratory, creating the very kinds of complex organic molecules that are considered the building blocks of life. It's like a snapshot of a prebiotic world, a frozen version of what Earth might have looked like billions of years ago, before life got started. It's a place preserving the chemical steps that could lead to biology, steps that were erased on our own planet long ago. For years, scientists had models predicting how this chemistry works, like having a recipe but never tasting the cake. They knew the ingredients, methane and nitrogen, and they could see the final product, the haze and the ethane lakes. But they were missing a key ingredient in the middle, something they knew had to be there but could never find. Until now. Enter the James Webb Space Telescope, or JWST. With its massive golden mirror and incredible sensitivity to infrared light, Webb can see into the cosmos with a clarity we've only dreamed of. It can see light from the most distant galaxies, study the atmospheres of exoplanets, and, as it turns out, stare right through Titan's thick haze to watch its chemistry in action. In a series of observations, Webb pointed its powerful instruments at Titan and saw exactly what scientists had been searching for. For the first time, Webb made a direct, definitive detection of a molecule called the methyl radical, or CH3. This might not sound like a headline-grabbing discovery, but in the world of planetary science, it's a huge deal. So what is a methyl radical? Let's break it down. A normal, stable methane molecule, the kind that fills Titan's lakes, is CH4. That's one carbon atom bonded to 4 hydrogen atoms. It's a happy, stable family. But high in Titan's atmosphere, when sunlight or particles from Saturn hit this methane molecule, they can knock one of the hydrogen atoms clean off. What's left is CH3, one carbon with only 3 hydrogens. This new molecule is missing a partner for one of its electrons, leaving it with an unpaired electron. This unpaired electron makes the methyl radical incredibly unstable and hyperreactive. It's desperate to grab onto something. This is what radical means in chemistry. It's a molecule that will react with almost anything it bumps into, and it does so very, very quickly. Because it's so reactive, the methyl radical doesn't stick around for long. It forms and is gone in a flash. This is why it was so hard to find, and why detecting it is such a triumph. Previous missions like Voyager and Cassini could only guess it was there. They saw the methane at the start and the ethane at the end, but the middle step was invisible. Webb's detection changed everything. Detecting the methyl radical isn't just about proving a theory. It's about understanding the engine that creates complexity on Titan. This one hyperreactive molecule is the cornerstone of a vast chemical network that turns simple gases into the building blocks of life. Let's follow a methyl radical, CH3. Once it forms from the destruction of methane, its main goal is to become stable again. The easiest way is to find another lonely methyl radical. When 2 of them meet, they join forces to create a new, stable molecule, C2H6, better known as ethane. This one reaction is incredibly important. It's the main way more complex hydrocarbons are built on Titan. You start with a 1-carbon molecule, methane, and end up with a 2-carbon molecule, ethane. This ethane eventually condenses and rains down, filling the vast polar seas that Cassini discovered. So, Webb's detection of CH3 is the smoking gun that connects the methane in the air to the ethane in the seas. But it doesn't stop there. The methyl radical is so reactive that it doesn't just make ethane. It reacts with all sorts of other molecules in Titan's upper atmosphere, helping to build propane, butane, and even more complex hydrocarbon chains. It also interacts with the nitrogen that fills the air, potentially forming nitrogen-rich organic molecules. These reactions are the first rungs on a ladder of chemical complexity. Step by step, simple molecules are stitched together into larger, more intricate structures. These are the very structures that, on a young Earth, are thought to have eventually led to amino acids, proteins, and the first living cells. This is the heart of why Titan is so fascinating for astrobiology. The processes happening in its atmosphere today might be a direct parallel to the prebiotic chemistry of early Earth. Before life, our own planet was a chemical factory, using energy from the sun and lightning to forge simple molecules into the complex stuff needed for biology. Life has since completely changed our planet, erasing almost all traces of that early chemistry. But Titan is like a preserved chemical fossil. It's a natural laboratory on a planetary scale where we can study these processes happening right now. This constant creation of complex organics, driven by the methyl radical, forms the thick, hazy smog that shrouds the moon. This haze is made of incredibly complex organic aerosols called tholins. These tholins slowly drift down and settle on the surface, covering everything in a layer of dark, organic dust that makes up the great dark dunes circling Titan's equator. This means Titan's entire surface is literally buried in the raw materials for life. The discovery of the methyl radical doesn't just shed light on Titan's present, it also gives us a peek into its past and its possible future. This constant chemical activity, powered by the destruction of methane, has long-term consequences. In a way, Titan is slowly consuming itself. Every time a methane molecule, CH4, is broken apart high in the atmosphere, its hydrogen atoms are released. While many recombine, some of the lightweight hydrogen inevitably escapes Titan's gravity and is lost to space forever. The carbon, meanwhile, gets locked up in heavier molecules like ethane or the organic haze, which then fall to the surface. Over millions of years, this process means Titan is irreversibly losing its methane. This brings up a huge question: is Titan running out of gas? The methane in its atmosphere isn't permanent. If it's not being replenished from somewhere, the sun will eventually break it all down. Without methane, the entire cycle of evaporation, clouds, and rain would stop. The lakes would dry up. The chemical engine in the sky would shut down. Titan would turn from the dynamic world we see today into a static, mostly airless ball of ice and rock. Does that sound familiar? It's a chilling parallel to Mars, which was once warmer and wetter but lost its atmosphere and water over billions of years. Is Titan on a similar path, just with methane instead of water? The answer hinges on whether Titan can restock its methane. Scientists think there might be a massive reservoir of methane locked away inside the moon, maybe in its icy crust or a deep subsurface water ocean. Cryovolcanism, ice volcanoes erupting slushy ice and methane, could periodically vent this trapped gas, recharging the atmosphere and keeping the cycle going. Now that we can measure the methyl radical, scientists have a new way to calculate just how fast methane is being destroyed. By comparing this rate to the amount of methane left, they can estimate how long the current supply will last. This will help us figure out if we're just seeing a temporary, methane-rich phase in Titan's long history. Methane is the lifeblood of Titan's fascinating chemistry, and understanding its ultimate fate is key to understanding the moon's entire story. The discovery of the methyl radical doesn't just shed light on Titan's present, it also gives us a peek into its past and its possible future. This constant chemical activity, powered by the destruction of methane, has long-term consequences. In a way, Titan is slowly consuming itself. Every time a methane molecule, CH4, is broken apart high in the atmosphere, its hydrogen atoms are released. While many recombine, some of the lightweight hydrogen inevitably escapes Titan's gravity and is lost to space forever. The carbon, meanwhile, gets locked up in heavier molecules like ethane or the organic haze, which then fall to the surface. Over millions of years, this process means Titan is irreversibly losing its methane. This all leads us to the ultimate question, the one that sparks our imagination whenever we look at this strange orange world. Could there actually be life on Titan? Let's be clear. Finding the methyl radical is not evidence of life. What it is confirmation that the chemical factory that could support life is humming along nicely on Titan. It proves the moon is a powerhouse for making complex organic molecules, the very ingredients of life as we know it. But just because you have flour and sugar in the cupboard doesn't mean a cake has been baked. The hurdles for life on Titan are huge. The most obvious is the brutal cold, around -180 degrees Celsius. Chemical reactions move incredibly slowly at those temperatures. Plus, the liquid on Titan's surface is methane and ethane, not water. Life on Earth depends completely on liquid water. It's the universal solvent that makes all the biochemistry in our cells possible. Could life exist in a liquid methane solvent? The simple answer is, we have no idea. If life does exist on Titan, it would have to be completely different from anything on Earth. It would need a different kind of cell membrane that wouldn't dissolve in methane. It would need a different metabolism, one that could work in the freezing cold, maybe by breathing hydrogen and eating organic molecules like acetylene, which are common on the surface. There are some tantalizing, though totally speculative hints. For years, scientists have noticed weird chemical imbalances on Titan. For example, models predict there should be more acetylene on the surface and more hydrogen in the lower atmosphere than we actually see. Could some bizarre, methane-based life form be consuming these molecules, just like life on Earth consumes oxygen? It's a wild idea, but far from proven. Another possibility is that life could exist not on the surface, but deep below in Titan's subsurface ocean. There's strong evidence that beneath its thick ice shell lies a global ocean of liquid water. While this ocean is probably very salty, it's possible that organic materials from the surface could get mixed in, maybe through melt pools from comet impacts. If that happened, you'd have the three key ingredients for life as we know it all in one place: liquid water, organic molecules, and an energy source. However, some studies suggest getting those surface organics down to the ocean might be really difficult, making it potentially nutrient poor. The discovery of the methyl radical makes Titan an even more compelling place to search for life, because it forces us to think outside the box. It reminds us that life might come in forms we can barely imagine, working with chemistry that is completely alien to us. Titan is the ultimate test case for just how weird life can be. What do you think is hiding under Titan's orange haze? Could a truly alien biology be thriving in its methane rivers, or is it a lifeless but beautiful chemical wonderland? Let us know your thoughts in the comments below. And if you're enjoying this journey to the frontiers of science, make sure to subscribe so you don't miss our next deep dive into the mysteries of the cosmos. The James Webb Space Telescope's detection of the methyl radical has opened a new window into Titan. We've gone from guessing to directly observing, confirming a key part of its atmospheric chemistry and sharpening our picture of how this prebiotic world works. But as powerful as Webb is, it can only tell us so much from millions of miles away. To really answer the big questions Titan poses, we need to go back, and that is exactly what we plan to do. In July 2028, NASA is scheduled to launch a mission unlike any other: Dragonfly. Dragonfly isn't a rover or an orbiter, it's a car-sized, nuclear-powered drone. After arriving at Titan in 2034, this revolutionary machine will fly through Titan's thick atmosphere, hopping from one spot to another. Its mission is to explore dozens of different sites, from the organic-rich dunes to the floor of an impact crater where liquid water from below might have mixed with the surface organics. Dragonfly is basically a flying chemistry lab. It will drill into the surface, grab samples, and analyze them with advanced instruments, searching for signs of prebiotic chemistry and, just maybe, the chemical signatures of life itself. It will build directly on the discoveries of Cassini and Webb, taking the next logical step from looking from afar to analyzing on the ground. It will land in a world drenched in the very molecules that Webb has now shown us how to trace. The discovery of the methyl radical is a pivotal moment in our exploration of Titan. It's a crucial piece of the puzzle that makes the Dragonfly mission even more thrilling. We are standing at the edge of a new era of discovery on a world that represents one of our best hopes for finding life beyond Earth. We don't know what we'll find, but the journey into Titan's mysterious orange haze has just begun, and the secrets it holds could change our understanding of the universe and our place in it forever.